All right, this is Mr. Bergman, and I'm going to be going over 4 practice problems to help you review for the momentum quiz that's coming up. These problems I took off of Khan Academy, and I also took a couple off of the AP Classroom course website. Keep in mind, there's a couple other topics you'll want to study in addition to these. You'll want to study the difference between an elastic versus an inelastic collision. And I also suggest working on a couple conservation of momentum problems. And you'll see an example of one of these in here. But you'll definitely want to try one that involves 2 objects colliding with each other. So here we go. So the first problem we have here, it says a volleyball falls on sand at time t equals 0 milliseconds and quickly comes to rest. The net force on the ball over this time is shown below. And we have a graph of force versus time. Force is on the y-axis and time is on the x-axis. And just to kind of illustrate what this graph is doing, it's going at a constant rate here of 9 newtons, and then it falls to 0 from 20 to 30 milliseconds. Now note this is in milliseconds. We do need to convert this to seconds if we're going to do a calculation. So there are 1,000 milliseconds in a second. So anyway, it's asking us what is the ball's change in momentum between 0 and 35 meters per second. So let's go ahead and just mark that here. This is looks like this is 35 and this is 0. So this is the total interval of time that we're looking at. Okay, well, let's think about basic momentum equations we have. We have 2 basic momentum equations. We have that momentum is equal to mass times velocity, and we also have the impulse equation. An impulse is a change in momentum, and it's equal to force applied to an object times the amount of time that force is applied. And this equation works really well when the force is constant, but here the situation, the force is not constant. So how are we going to find the change in momentum if we don't have a consistent force? Well, if you look again at the y-axis, this is the force and time is the x-axis. So really, if we find the area under the curve, or the graph in this case, that's actually going to give us the change in momentum, because force times time equals change in momentum. Now, the shape of this graph is fairly basic. We can break this up into 2 main things, a rectangle, and we can create a triangle. So to find the area of this rectangle here, we're just going to take the base, which is the time interval, and multiply it by the height, which is the force. And coincidentally, this is how you normally use this equation. This represents a constant force, right? So 2 newtons times the interval of time that's applied, and you get your answer, right? So anyway, we'll find the area. Base is not 20, but 0.02, because there are 1,000 milliseconds in a second. And then the force is going to be 2 newtons. And for this area, we're going to get 0.04 newton seconds as our answer. Now we do that for the next one here. This is a triangle, so we're going to use the area of a triangle equation, 1/2 times base times height. So 1/2 times the base, which is 20 to 30, and again, that has to be converted to seconds, so that's going to be 0.01 seconds. And then we multiply that by 2 newtons, and for this one, we get 0.010 newton seconds. Now, our answers get added together because, again, it wants the total change in momentum from 0 to 35. So when we add them together, we get 0.050 newton seconds as our change in momentum. All right. Let's take a look at the next problem here. This problem is a multiple choice question. So before I talk about how to solve it, let's read the question and look at the answer choices. It says a ping pong player serves a ball to their opponent. The net force on the ball over time is shown below. So very similar, right? We have a force graph versus time. Notice that the force is 0 at first, and then it cranks up to 1.5 newtons for an interval of, looks like 30 milliseconds. Now the question says, how does the ball's velocity change between 30 milliseconds and 60 milliseconds? So at first, this problem looks like it's set up to calculate, kind of like what we have up here, but notice the answers don't actually require us to do any calculations. All we have to identify really is whether the ball's velocity increases, then decreases, or whether it just increases the whole time, whether it just decreases, or that the velocity of the ball does not change. So if we take a look at this, we can again identify that the change in momentum equation is force times time, but we also know that the change in momentum can be equal to the mass times the change in velocity. If we put these two equations together, we can create an equation that says mass times change in velocity is equal to force times time. And as you can see here, it's asking us what the ball's velocity changes. So really, we're just being asked what this is. Now, we don't know the mass of the ball, but we do know the mass is constant, so it's not really going to be affecting the change in velocity. The force, however, does change over time, and the time is the given interval. So it's a constant as well. It's going to be this interval right here. It's the 0.030 seconds. So really, all we have to do is look at the force here to determine what's going to happen to the velocity, because mass is constant, time is constant, and they also don't have a direction, so they don't really tell us anything about whether it's going to gain velocity or not. It's really the force. So let's look at the force. The force is positive, right? The whole time this interval is occurring, the force is positive. They don't tell us the ball has a velocity. You know, we can probably assume it's at rest because it's going to be hit by the ping pong player. So the force that the ball is going to get is it's going to be a force that causes it to get faster. So when we look at the options here, really the only answer that we have is that B, the velocity increases, will definitely be our answer. Now, if we had a graph that said or showed the graph going into the negative realm, then that might be a case where we could say, okay, look, the force will be negative for a period of time. That would cause the velocity to go down in this case, assuming the ball had a positive velocity. If the problem also stated that the ping pong started with a negative velocity, well, because it's receiving a positive force during this time interval, that positive force is in the opposite direction of its velocity. So that would actually cause its velocity to become more positive. So the speed would slow down. It would decelerate the ball. But these are just a little bit more advanced kind of ideas. Let's just stick with the basics here. The ball is receiving a force, and that force is going to cause its velocity to increase because of the equation. Velocity is proportional to force. The greater the force and the longer the time it's applied, the greater the velocity will become. Okay, so let's go to the next page here. I've got a problem that's a little bit more complex to set up, and I got a couple ways to explain this one. So we have a 50-kilogram person standing still in ice skates, and they throw their helmet to the right at 25 meters per second while on a frictionless surface. This gives the person a speed of 1 meter per second leftwards. Now, what you want to recognize when you see a problem like this is that this is a conservation of momentum problem. And the best way to identify that this is one, typically, is that you have two objects, right? We have a person who's moving to the left, and we have an object that gets thrown, an object that moves to the right. Now, it's really useful, I find, for conservation of momentum problems to draw a little picture. So we start with a person, they're at rest, they're standing still, right? And they're holding this little helmet thing. Now, afterwards, they throw the helmet to the right. Now, momentum-wise, the helmet gains positive momentum if we say positive is to the right. Conservation of momentum says that in any type of collision or interaction in a closed system, the total momentum has to be zero. The change in momentum of the system is zero. So if we sum or add up all the momentums of all the objects in the system before something happens, and we add up all the momentums of the objects after something has happened, the total change in momentum of the system needs to be zero. So in other words, if this helmet gains positive momentum, the person will have to gain an equal but opposite or negative momentum. So this is a way of representing this. We can also say that the total momentum before the collision, represented by the not symbol, is equal to the total momentum after the collision, represented by the F or final. So initial and final. Momentum before equals momentum after. All right. Now, with our picture here, we can kind of set up all the objects that have momentum before and all the objects that have momentum after. So we have a person that has momentum, the not again symbolizing the initial condition before the collision or the thrown helmet. We have the helmet and its momentum before it's thrown. Now keep in mind the person and the helmet are at rest, so these momentums actually cancel out. There's zero. They don't have any momentum. After the helmet is thrown, the person will have a momentum, a final momentum, and the helmet will have a final momentum. So this equation represents what exactly is happening. And we're given lots of masses and velocities, and a very useful substitution that will help us answer this question is simply the equation momentum P is equal to mass times velocity. So we're going to substitute that in. Now remember, we said there is no momentum at the beginning of the system, and that's important to know because after the system, the momentum should also be zero. So this term and this term should add up to zero. That means one of them must be negative, and they also must be equal to each other, right? So when we substitute the momentum of the person after the collision, momentum of person final, we're going to have the mass of the person times the velocity of the final velocity of the person, plus the mass of the helmet times the final velocity of the helmet. Okay? Now, ultimately, remember the problem is asking, what's the mass of the helmet? So I circled this one, and we need to move these algebra terms or these variables to the other side so we can solve for the mass. And to do that, we're going to first start by subtracting this term. And so we're going to go minus the mass of the person times the velocity, the final velocity of the person. And that's going to move this term to the other side. And then to separate the mass from the final velocity of the helmet, we have to divide. And so that's ultimately going to create what we have over here. The mass of the helmet is equal to, because we subtracted, negative times the mass of the person times the final velocity of the person, divided by the final velocity of the helmet. And so when we plug these in, negative 50 is the person's mass, negative 1 meters per second. Keep in mind, it says speed, so speed doesn't have direction, but it says left. So remember that because it's left, it should be negative since we're saying right is positive. So that's where the negative sign came from. And then we're going to divide by 25 because that's the velocity that the helmet was thrown. And I made that a positive number because, again, the helmet was thrown to the right. So it's the opposite direction. So anyway, we do the calculation. We get 2 kilograms. That's the mass of the helmet. Now, this is, I showed this method because this general method, this is essentially an equation for a system of 2 objects. And this will work for pretty much any type of elastic collision. So if balls are bouncing off each other, anything like that, this will work for the most part. And you don't necessarily need to go this whole step to kind of understand this problem. Remember what we said, that the momentum that the person gained has to be equal to the momentum that the helmet gained. This is a negative value because the momentum gained is in the negative direction. This is a positive value because the momentum gained is in the positive direction. These two things, when add up to 0. So we know that the magnitude of these momentums are the same in order for momentum to be conserved here. So remember that momentum is mass times velocity. So if we know that the person, 25 times 1, has a total momentum of 25, then we know that the helmet must also have a total momentum of 25. So when we're told that I'm recording this live, so I can't come back and edit this. The person's mass is 50, right? So 50 times their velocity of 1. So 50 units of momentum is actually what I meant to say. So here, for the helmet, we're told that the helmet has a velocity of 25. Now, because the momentum of the helmet, its magnitude must be the same for momentum to be conserved, we can kind of think, okay, what must the mass be to times it to create the number 50? Well, it must be 2. 2 times 25 is equal to the same momentum that the person got to the left. So that's just just a quick way of showing how to solve a problem like that and kind of thinking about that. Okay, now we got the last problem that I'd like to share with you guys. This is another multiple choice problem. It says a toy car of mass 2 kilograms travels along a horizontal surface with a negligible, so very little, friction. We assume that means none, or we can just kind of disregard it. So it travels along a horizontal surface at a speed of 1 meter per second. The car then collides with a vertical wall. The wall applies a force of magnitude 20 newtons for 0.2 seconds on the toy car. Which of the following predicts the motion of the toy car immediately after the collision? So this one is an interesting problem. And like I said before, it's great to draw a little picture of the system so you can kind of see what's happening. We're starting with a car. It's moving towards a wall, so it has a velocity. It also has momentum because momentum is mass times velocity, right? It crashes into the wall, bang, and the question's basically asking us to predict what the motion of the car is after the collision. So does the car crash? Does it stop? Would it be like an inelastic collision? Or does it bounce off, kind of like an elastic collision, where some of the kinetic energy or maybe even all of the kinetic energy is conserved? So how do we figure this out? Well, we can think of this problem in terms of impulse. When the car collides with the wall, it's going to receive an impulse or a force applied from the wall to the car that's going to cause a change in momentum. So an impulse is a change in momentum, and in this case, the force from the wall to the car will happen over a period of time. And they give us these values. 20 newtons is the force that the wall exerts on the car, and it will exert it for 0.2 seconds. So we actually know that the change in momentum of our car is 4 newton seconds. That's the change in momentum. So we can think about that. Okay, well, the car must have had a positive momentum before it collided with the wall. The force that the wall is going to exert on the car is going to be in the left or negative direction. So although I calculated a magnitude here, we really want to think of this as a negative gain in momentum. It's going to be forced, or an impulse is going to be on the car from the wall to the left. So certainly the car is going to lose positive momentum and it's going to gain negative momentum. So when we look at our answer choices, we want to think, okay, can we eliminate anything, or do we need to continue and kind of think about this problem? Which of the following predicts the motion of the toy car immediately after the collision? The speed of the car will increase and the car will travel in the opposite direction. Now, we can't rule this one out because, as we said, it makes sense. The car is going to, if it's getting an impulse, boom, there's a chance it might bounce off and go in the opposite direction. Okay, the next one, the speed of the car will decrease and the car will travel in the opposite direction. We can't rule this one out either because, again, it makes kind of sense. The speed of the car will remain the same and the car will travel in the opposite direction. Okay, this one kind of makes sense too. The car will stop and remain motionless. Now, this one kind of makes sense as well because, if the car just crashes, if it gets a change in momentum that's equal to the momentum it had before hitting, then it's just going to stop. So unfortunately, we can't rule anything out. We're going to have to go a little further. Now, fortunately, the problem tells us information that can lead us to figuring out the original momentum of the car. It has 2 kilograms of mass and it's traveling with a speed or velocity of 1 meter per second. So we know that the total and change in momentum of the car from colliding with the wall is 4 Newton seconds. But the original momentum of the car is 2 Newton seconds. By the way, the units of momentum are either Newton seconds or kilogram meters per second. It doesn't matter which one you use. So anyway, here's the idea. If the car receives an impulse from the wall in the opposite direction that it's going, then its change in momentum is going to make it ultimately have a negative momentum, right? It starts with positive 2 momentum. It's going to gain negative 4 momentum because that's the change. So the final momentum that the car will have will be negative 2 Newton seconds. Now, this tells us that D is not possible because if the car ends up with some value of momentum, it's not motionless. It also tells us, because it has the same magnitude of momentum and the mass of the car is the same, that it's not going to be going any faster and it's not going to be going any slower. So the best choice we can pick here is got to be C. The speed of the car will be the same, except now it's going to be going in the opposite direction. And this is an example, this is a great example of an elastic collision. Kinetic energy remains conserved because the car is moving the same speed that it was, and kinetic energy is 1/2 mv squared. So the car still has all of the energy that it had before the collision. Now, the reason why I bring up kinetic energy because it really helps us rule out A from the get-go. A says the speed of the car increases. And keeping in mind that even in an elastic collision, kinetic energy has to be conserved, there's no way that you can create kinetic energy. And if the car got faster, that means somehow there was more kinetic energy after the collision than before the collision. So the fact that this is telling us that the speed of the car will increase is questionable. And you really want to think, how could it be possible for a collision to increase the speed of the car? That would violate conservation of energy. You can't create energy. And it's not like there's any potential energy that's this energy is coming from. So yes, the answer is C here. So I want to wrap it up. Anyway, I hope that some of these questions will help you study, and remember my advice about other topics to study. All right, good luck.